Okay, so let us start today's session. Hello everyone, welcome to the week 3 problem solving session for the pattern recognition and application course. I am Tanuka Bhattacharjee from IISc Bangalore. I am pursuing PhD in the electrical engineering department there. So in today's problem solving session, we will solve a few more problems on Bayesian classifier, discriminant functions and normal distribution. So let us get started with the first problem. So this is the first one. It says that consider a two-class problem . Consider a two-class problem with one-dimensional feature space. And let the class conditional densities be. So the two classes here we are assuming as omega 0 and omega 1, and we have one dimensional feature space. So it's just let us represent that by x. Now the class conditional densities for the two classes are given. So given omega naught, that the class is omega naught, the distribution of x is given as exponential distribution for positive x. And so since it is given that the distribution is a to the power minus x for x greater than 0, we will assume that for x less than equal to 0, the probability distribution will be 0. And for the class omega 1, the probability class conditional density for x given omega 1 is given by 1 by 2a, which is defined in the interval minus a to a. Outside this interval, the probability is 0. So if it means that if we are sampling a feature vector or a feature value, since it is one dimensional, I should not say feature vector, it is one feature value from class omega 1, then it is not likely to have the value below minus a or above plus a. It will be within the region minus a to a. Outside that, the probability is 0, it is not likely to come from there. These are the two class conditional densities provided, and it is said that the prior probabilities are equal. That means p of omega 1 is equal to p of omega 0. So the two classes are equally likely. The prior probabilities are equal. Now we are asked to assume that we are using a 0-1 loss. So what does 0-1 loss means? That if we correctly classify a sample, then the loss is 0. If we make any mistake, the loss is 1. So if we write it in terms of lambda function, the notation we use for the loss, so let's say here lambda 1 1 will be 0 and lambda 2 2 will be 0, whereas lambda 1 2 is 1 and lambda 2 1 is also 1. So here, as you all will know, lambda ij means this is the loss of taking action alpha I given the true class is omega j. So here we are assuming the actions as being classified in class omega 0 or class omega 1. So alpha 0, this action corresponds to being classified in the class omega 0, and alpha 1 corresponds to classifying in class omega 1. So alpha ij, a lambda ij is basically the loss of classifying in class I when the true class is omega j. Class omega I when the true class is class omega j. Now the question is, find the Bayes minimum risk classifier, and for the case when a equal to 0.25, find the probability of error. So let us start with finding the Bayes minimum risk classifier. So as we know, the expression for risk is given as risk of taking the action alpha I given that the feature is x this is equal to summation the loss of taking the action alpha I given that the true class is omega j into the posterior probability of omega j given the feature value x, and the summation will be over j. Since here we have two classes, it will be over 0 and 1. So, this is the general expression for the risk. So, as we said, alpha 0 corresponds to being classified. So, this means we are classifying x as element of omega 0. This is our prediction. In that case, what is the risk of the action alpha 0 given x? That will be given as summation j equal to 0 to 1 lambda alpha 0 given omega j into p omega j given x. Now, if x truly belongs to omega 0, then the loss is 0, and if it belongs to omega 1, then the loss is 1. So, in this summation the term lambda alpha 0 given omega 0 into p omega 0 given x, that will not appear, since lambda alpha 0 given omega 0 will be 0. So, the only term that will appear is lambda alpha 0 given omega 1 to probability of omega 1 given x, and the loss of taking the action alpha 0 when the true class is omega 1 is 1. So, this risk will in turn be the posterior probability of class omega 1 given the feature value x. Similarly, we can compute the risk of taking action alpha 1 given the feature value x. So, in this case the expression will be summation j equal to 0 to 1 lambda alpha 1 given omega j into p omega j given x. Now, when we put j equal to 0, so lambda alpha 1 given omega 0, that is 1 because that is a misclassification. So, we will have that term, and the other term when we put j equal to 1, that is lambda alpha 1 given omega 1, that is correct classification. So, that loss is 0. So, we will not have that term. So, these will be the two risks. Now, since we are asked to do the minimum risk classifier, so that means we will take the action alpha 0 if the risk of taking that action is minimum. So, we will take the action alpha 0, that is we will classify x as omega 0 belonging to omega 0 if the risk of taking the action alpha 0 given x is less than the risk of taking the action alpha 1 given x. Okay. So, if we just put these two expressions of risk of taking action alpha 0 and risk of taking action alpha 1, then this expression becomes p of omega 1 given x should be less than p of omega 0 given x in order for x being classified to omega 0. Now, these are the posterior probabilities. We can write this, let me write it down once more. P of omega 1 given x should be less than p of omega 0 given x for the action alpha 0. Yeah. Now, these are the posterior probabilities. So, we can express this as p of x given omega 1 into p of omega 1 divided by p of x, and that should be less than p of x given omega 0 into p of omega 0 divided by p of x. Since p of x is a positive quantity and it's present in both sides, we can simply cancel this out. Also, it was mentioned in the question that the prior probabilities are equal. So, p of omega 1 and p of omega 0 are also equal and they will be positive. So, we can cancel this also. So, the final condition that we have is p of x given omega 1 should be less than p of x given omega 0 for taking the action alpha 0. So, now we are if you see the question, these two class conditional densities has been specified to us. So, p of x given omega 0 is e to the power minus x for x greater than 0 and p of x given omega 1 is 1 by 2a for x element of minus a to a where a is greater than 0. So, if I plot these two class conditional densities, how will they look? So, first class conditional density for class omega 0, this is a exponential function e to the power minus x for x greater than 0. So, this will be the curve for the class conditional density of omega 0, and for other one it will be, let us say here, let me take one other color. So, here let us say it is minus a and this is a. So, density is like this, it is uniform. Okay. It is uniform, and so this one is p of x given omega 1. So, now if we let us look again into the expression that we have, that for taking action alpha 0 we should have probability of x given omega 1 less than probability of x given omega 0. Similarly, for taking the action alpha 1, the condition will be reversed. So, p of x given omega 0 should be less than probability of x given omega 1. Okay. So, here if you see in the, this is the x axis. So, if you see in the negative region, here the probability of x, the class conditional density of x given the class is omega 0, that is 0, and from the region minus a to 0 we have some finite probability of the class conditional density of class omega 1. So, there is no chance that the feature value will come from this region below minus a, but for the sake of completeness to define the classification result or the classifier output for the entire region, we can simply put this region, or consider this region also having the similar action as the next this region minus a to 0. So, here you can see that always the probability of x given omega 1 will be higher than the probability of x given omega 0. So, in this region the decision will always be alpha 1, that is x belongs to omega 1, right. So, because for alpha 0 this probability of x given omega 1 should be low, for alpha 1 the probability of x given omega 1 should be high. So, in this region it is always high. So, we can take the action as alpha 1 for this region. Now, if you consider this region a where x value is higher than a, there the class conditional density for class omega 1 is 0, whereas that for class omega 0 is having some finite positive value. So here always the probability of x given omega 0 will be higher. So for this region we will always take the action as alpha 0. Now the question remains for this portion, for 0 to a, what will be the case. Now if you see the probability, conditional probability density, this one, a to the power minus x, and x is positive. So you can see that this value is always less than 1. So p of x given omega 0 is always less than 1. So if we have such a value of a such that 1 by 2a value is always greater than equal to 1, in that case we will always take the action omega alpha 1. So what will be the condition for that? So we need this to be always greater than equal to 1. So if our, that means our a has to be less than equal to half. So if your a is less than equal to half, then whatever be the value of x, you will always have higher value of probability, the class conditional density of class omega 1 than the class conditional density of class omega 0. So if a is less than half, then probability of x given omega 0 is always greater than, if a is less than equal to half, then 1 by 2a is always greater than equal to 1. So your probability of x given omega 1 is always greater than your probability of x given omega 0. Okay. So you will always take the decision as alpha 1. Now this is for this region from 0 to a. So if a is less than equal to half, for the 0 to a region, you will your this condition will always hold, and you will take the action as alpha 1. So in that case the classifier will be simple. So if I'll write one final statement for this case here. So if a is less than equal to half, in that case you will take the action alpha 1, that is, you will say that x is element of class omega 1 if x is less than equal to a, if x is less than equal to a, and otherwise you will take the action alpha 0, that is, x is element of class omega 0. Okay. Now let us take the other case when a is greater than half. If a is greater than half, then in that case you will take the decision for these regions, the negative value of x and the value of x higher than a remains the same, but for this region 0 to a, you will take the decision as alpha 0 if you have probability of x given omega 1 less than x given omega 0. So alpha 0 will be if x given omega 1 is less than So your x given omega 1 is 1 by 2a, that should be less than e to the power x. Then you will take the action alpha 0. So if you take the log on both sides, it becomes minus ln of 2a should be less than minus x, or your x should be greater than ln of 2a. So if your x is greater than ln of 2a, then you will take the action alpha 0. No, sorry. X should be less than ln of 2a, then you will take the action alpha 0. So if it is less than ln of 2a, then you will take the action alpha 0, because you have to change the side because of the sign. So if x is less than ln of 2a, you will take the action alpha 0. If it is greater than ln of 2a or greater than equal to ln of 2a, then you will take the action alpha 1. But this is for the portion 0 to a, this region only. So even if your a x value is greater than ln of 2a, it should be less than a, then only this expression, this decision rule holds. So here for a greater than half, your decision rule will be like this. Your decision rule will be like this. For a x less than 0, you have alpha 1. Okay. For x less than 0, you have alpha 1, that is x element of omega 1. Now for 0 to ln of 2a, 0 to ln of 2a, you have the action alpha 0, that is x element of omega 0. Then from ln of 2a to a, you have the action ln of 2a to a, you will have the other action, that is alpha 1. So x is element of omega 1. And lastly, above 2a, you have the action alpha 0. So if x greater than a, you have the action alpha 0, that is x element of omega 0. So this is the classifier rule for the case a greater than half, and this below one is the classifier rule for the case x a less than equal to half. So this is the Bayesian minimum risk classifier for this particular situation. But we have one more part in the question, that for the case when a equal to 0.25, find the probability of error. So let us take the case that a equals to 0.25. In that case, a is less than half. So our classifier will be following this rule. So we will put x in omega 1 if x is less than equal to 0.25, x less than equal to 0.25, we will put x in omega 1, and if x is greater than 0.25, we will put x in omega 0. So now what will be the probability of error given x? That will be, since in this region x less than equal to 0.25, you are taking the action that x is element of omega 1. So the probability of error given x will be and it will be probability of omega 1 given x when x is element of omega 0, right. So if you want to compute the probability of error, that is, as we know, integration probability of error given x px dx, that will be the complete probability of error for all value of x minus infinity to infinity. Now, so when you have x less than equal to 0.5, you are taking the decision x element of omega 1. So your corresponding probability of error is becoming probability of omega 0 given x. So for minus infinity to 0.25, this is probability of omega 0 given x dx dx, and after that 0.25 to infinity, you are taking the action x element of omega 0. So the probability of error given x is probability of omega 1 given x. So this is becoming this. Now, since we do not know the posterior probability, we again need to convert it to the class conditional. So this is equivalent to this, and this is equivalent to right. Now I'll do the rest of the part here. Okay, so probability of x given omega 0. Probability of x given omega 0 is e to the power minus x for x greater than 0. So this integration will become 0 to 0.25 e to the power minus x, and since both the classes are equiprobable, probability of each class will be half. So half dx. Now for the next term 0.25 to infinity, we have this. Now 0.25 is basically the a value. So a to infinity, we have probability of x given omega 1 into p of omega 1. Now probability of x given omega 1 is defined for minus a to a. Above that it is 0. So we do not need to consider this term. So this will simply become So this will be the final probability of error. This was one more example of making the Bayes minimum risk classifier, where the two class conditional densities have been specified, the prior probabilities have been specified, and the loss function has also been specified. Then this is the procedure that you can follow to derive the classifier as well as derive the probability of error for that classifier. Now let us move on to the next problem. The next problem is this. This is on discriminant function for normal density. So here it is given that 4 samples are given for the class omega 1 and 4 samples are given for the class omega 2. So we can see that the feature vectors are 2D. The feature vectors are 2D. We have two classes, omega 1 and omega 2, and these are some training samples from both the classes. The first question is, compute the mean vectors and covariance matrices of the two classes. This is a simple one. First let us compute the mean vectors. Let the mean vector be mu1 for class omega 1 and mu2 for class omega 2. So for mu1, the mean vector will be You can simply take the average of the 4 training samples, that will be the mean vector for that class. Similarly, for class omega 2, the mean vector will be (8,1). These are the two mean vectors of the two classes. So it's simply the average of the 4 training examples. Now we need to compute the covariance matrices. So what is the expression for covariance matrix? Let's say general covariance matrix sigma I. The expression is expectation of x minus mu y into x minus mu y transpose. This is the general expression for the covariance matrix. Now let us first before that, so here we are the expression is given in terms of expectation, but since we have finite number of examples, we will express expectation by the sample mean. So we will simply have 1 by, let's say n is the number of samples in that class, summation of j equal to 1 to n xj minus mu y to xj minus mu y transpose. Okay, let us compute this for the first class. So we are computing sigma 1. So this will be 1 by 4 because we have 4 samples, summation j equal to 1 to 4 xj minus mu 1. What was mu 1 in this case? Mu 1 was 2 1 minus 2 1 to xj minus 2 1 transpose, summation of this thing. So let us first compute the term within the summation for all values of j. We will take different values of j corresponding xj and xj minus, let me just write mu 1 into xj minus mu 1 transpose. So for the first one, I will just copy this first, 1 1 2 0 2 2 3 1. These are the 4 examples. 1 1 2 0 2 2 and 3 1. These are the 4 samples we have. So what will be this expression? This will be minus 1 0 minus 1 0 transpose. So if we do the product, we will get our 2 cross 2 matrix, and the matrix will be 1 0 0 1 0 0, yeah, 1 0 0 0. Similarly for the next one, the xj is 2 0, mu 1 is 2 1. So we have the xj minus mu 1 as 0 minus 1 and 0 minus 1 transpose. We get the matrix as 0 0 0 1. Similarly for the next one, we have to do here, this is 0 1 0 1 transpose. So the matrix will be 0 0 0 1 again. And the last one is 3 1, xj is 3 1. Here xj minus mu 1 will be 1 0 and 1 0 transpose. So the matrix will become 1 0 0 0. So we have computed all the terms within the summation. So the final sigma 1 will be just 1 by 4 times the summation of these 4 matrices. So if we take that summation, it will be 2 0 and 0 2. So it will become half 0 0 half. This is the covariance matrix of the first class. Okay. Similarly, we have to now compute the covariance matrix of the second class. So for the second class, we have already computed the mean as 8 1, and the 4 samples that we have are 6 1, 8 minus 1, 8 3 and 10 1. So here if the expression that you will have for omega 2 will be, again you have 4 samples, summation j equal to 1 to 4 xj minus mu 2 xj minus mu 2 transpose. So here again let us do the same business. And mu 2 is 81. So here you will have minus 20 transpose, it is 4000. Then you have 0 minus 2 transpose, that is 0004. Then you have 02 transpose, so again 0004, and lastly 20 transpose, that is 4000. So going by the similar formula, we will have to sum up these 4 matrices and divide each element by 4. So the final value that you will get is 2002. This will be the covariance matrix of the second class. So this was the first part of the question. Now it says, assume that the classes are normally distributed and equiprobable. So equiprobable means probability of omega 1 is equal to probability of omega 2. Let us say Bayesian minimum error rate classifier is being used. So in that case, as you would remember from the lecture, that when we have Bayesian minimum error rate classifier, if we want to have the discriminant function for, let us say, class I, that will be nothing but probability of omega I given x. Right. So this will be the discriminant function for the ith class, that is the posterior probability of that particular class will be the discriminant function. So for which the posterior probability is higher, we will classify in that class. So we have to now determine the decision boundary. So as you know, at the decision boundary, the discriminant function value for both the classes are equal, that is g1x, which is the discriminant function for class 1, minus g2x, which is the discriminant function of class 2, that is equal to 0 on the decision boundary. So we can solve this to obtain the equation of the decision boundary. For that, let us first compute g1x minus g2x. So this will be equal to probability of omega 1 given x or, since this is a normal distribution, taking the log will simplify the things down, because normal distribution, you know, you will have exponential function. So if you take the log, things will become more simplified, and we also know that if we take a monotonically increasing function of some discriminant function, it again remains the discriminant function. So instead of taking this as the discriminant function, we will take the discriminant function as log of this. That will simplify our computation a lot. So we will have a log here. This will be the expression. So we can simplify this further. We can write this as probability of x given omega 1 into probability of omega 1 by p of x Now the denominator is present in both the terms, it equally, the value is equal, so it will cancel out. Also we have that the two classes are equiprobable, so the terms with probability of omega 1 and probability of omega 2, these two will also cancel out. So the final expression that we will have is ln of the class conditional of class omega 1 minus ln of the class conditional of the class omega 2. Okay. Now these two class conditionals are given as normal distributions. So let's say first simplify this even more. So if we put the expression of normal density, let us first write the expression for normal density. So for the first class omega 1, the expression will be 2 pi to the power d by 2, where d is the dimension of the feature vector, sigma 1 determinant to the power half exponential minus half x minus mu 1 transpose sigma 1 inverse x minus mu 1. Now since we have the ratio of px given omega 1 by px given omega 2, the first term, that is 1 by 2 pi to the power d by 2, that will be present in both the expressions, so that will cancel out. So we will not have that 2 pi term. The first term that we will have is from this sigma, the covariance term. So we will have that ratio. Then you have the exponential. So exponential of one term divided by exponential of other term from the two density functions. So this will basically become exponential of the term coming from class omega 1 minus the term coming from class omega 2. So this will become exponential of this. Now if we apply the log function on this, we can simplify it as determinant of sigma 2 was 2002, so the determinant will be 4, the product of the diagonal terms. So 4 divided by the determinant of omega 1, sigma 1 was half 0 0 half, so product is 1 by 4, determinant is 1 by 4. So half. or we can put the half outside. This plus log of exponential, that will cancel out, we will have just the term within exponential. So this will become this. So now let us simplify this even more. So let me take x as the two elements as x1 and x2. So this will become x1 minus, so mu1 was 2 1, mu2 was 8 1. So x1 minus 2, x2 minus 1. So I am just assuming x equal to x1 x2 like this. So this transpose sigma 1 inverse, sigma 1 was half 0 0 half, so its inverse will be 2 0 0 2. Again x1 minus 2, x2 minus 1 plus, similarly for the other term. Here sigma 2 was 2 0 0 2, so it will be half 0 0 half. If you simplify this further, you will get that will again be equal to, if I simply take the half out, square. So I am not going into further simplification right now. So the expression of the decision boundary, this is we have computed g1x minus g2x. So the decision boundary will be this equal to 0. So the decision boundary will be This will be the decision boundary. You can further simplify it down. Now let us move to the last part of the question. The last part is classify an unknown feature vector x 4.51 transpose into the class omega 1 or omega 2. So we have the expression for the decision boundary is g1 minus g2x equal to 0. So g1 minus g2x is given by this expression. So we will classify a feature vector in class omega 1 if g1 will classify x as omega 1 if g1x is greater than g2x, that is g1x minus g2x is greater than 0. Here the expression that we have for the decision boundary, this is basically the g1x minus g2x expression. So if we put the x value in this and it comes out to be greater than 0, then we will classify x in omega 1, otherwise we will classify x in omega 2. So here the x that we have is 4.51. So we can simply put this value in this particular expression to see whether it is greater than 0 or less than 0. So let us do that. Minus this will be 2.5 square. This term x2 minus 1 square will become 0 plus 1 by 4, it is minus 3.5 square, plus again this term will be 0. Can any of you please compute this and tell me the answer? Okay, let me just tell the final value. It will be around minus 1.8 approximately. So we see that the value is negative. So if the value is negative, that means g2x is greater than g1x. So x we will classify as element of class omega 2. So if we have got this expression value as greater than 0, then we would have classified x in the class omega 1. We will quickly move to some small problems. I am skipping one problem here that is on binary features. I will take that up in the next class. So in this problem, it is given that we are considering a 2D Gaussian density with covariance matrix sigma given as this matrix, and the locus of the points of constant density is shown in the figure. Now which of the following is or are correct, we have to say. So here we have 2D feature vectors x1 and x2 are the two dimensions, and we see that the locus of the points of constant density is a circle. So immediately that means that x1 and x2 are statistically independent. In that case only the major axis and minor axis will be parallel to the two feature axes, so that they are statistically independent. That's when the case. So that's when the two axes, major and minor, will be aligned with the two feature axes. Now if that is the case, these two features are statistically independent, then the covariance of sigma 1 2, that is the which captures the relation between the feature 1 and feature 2, that will be 0. So, the fourth condition sigma 1 2, that will be 0. Similarly, sigma 2 1 also will also be 0. Actually, these covariance matrices that we have are symmetric matrices, right? The sigma 1 2 and sigma 2 1 are in essence the same, because sigma 1 2 is expectation of x1 minus omega 2 into x1 minus omega 2 square. Similarly, the other one is also sigma 1 2 is basically expectation of and sigma 2 1 is. So, since these are single elements only, there is no meaning of putting transpose over there. And this is expectation of x2 minus mu2 to x1 minus mu. So, these are in essence the same. So, it is symmetric matrix. So, this is also true. And since this is a circle, that means the variance of both the features are equal. So, sigma 1 1 and sigma 2 2, those are the variance of each feature, those are also equal. So, this one is also true. Now, if we have like this, the ellipsoidal figure, again the two major and minor axes are parallel to the two feature axes. So, the two features are statistically independent and sigma 1 2 is again 0. Sigma 1 2 equal to sigma 2 1 is always correct, because it is a symmetric matrix. And here, since this is ellipsoid, that means the covariance of the variance of x1 is higher than variance of x2, or sigma 1 1 is higher than sigma 2 2, that is they are not equal. So, this is the correct answer. And lastly, again we have the ellipse. So, following the previous argument, here also sigma 1 2 not equal to sigma 2 2, sigma 1 1 not equal to sigma 2 2. The matrix is symmetric, so sigma 1 2 equal to sigma 2 1. And lastly, the major and minor axes are not parallel to the two feature axes. So, the two features are not statistically independent. So, sigma 1 2 here will not be 0. So, these two are only the correct answers. Okay. So, if any of we are already out of time, still if you have any questions, I will wait for 1 minute. If you have any questions, you can put it in the chat, I will take that up. Okay, I don't see any questions. So, that was it for today's session. Let's meet again in the next week with the next set of problems. Thank you everyone.